Hello everyone from Math 2000, Linear Algebra. Professor Wenson here again with a video on your Zybooks section 7.5. This is on the composition of linear transformations. And you're going to see that it's very similar to composition of functions that you most likely learned in a pre-calculus class or some prior algebra class. So they start off by saying exactly what I just said, For real valued functions, function composition is defined by, this, remember this like little O symbol? This meant f composed with g of x, or f of g of x. You could write it this way as well. So hopefully that looks familiar to you, because it's coming back here, but this time instead of just, functions between the real numbers, we're going to look at, transformations between vector spaces. So yeah, the same notation and operation can be applied to linear transformations. In fact, the composition of two linear transformations yields another linear transformation. And that'll be shown later. I'm not going to go through that proof, but just know that when you compose two linear transformations, the result is also a linear transformation. And since a linear transformation can be represented by a matrix, remember the matrix, standard matrix, the composition of linear transformations can be obtained by multiplying the matrices that correspond to the linear transformations that you composed. Alright, so we have the objectives here, what you're going to be expected to know how to do by the end. Alright, the first part of this section is on properties of compositions of linear transformations. Okay, so we have this transformation T1 from vector space U to vector space V, and T2, another linear transformation, but from vector space V to vector space W. Then their composition, right, the composition of T2 with T1 is denoted with this notation, T2, little O symbol, T1, that's T2 composed with T1, is the transformation defined by this, as T2 composed with T1 of some vector U is, T2 of T1 of U. Right, so remember what happens in composition. I take my vector U, I would apply transformation 1 to that, and then I take this vector, whatever T1 of U is, and then apply transformation T2 to that. And so basically it's just a series of consecutive substitutions. And they have a little picture here showing you what's going on. Right? Say this blue area represents vector space U, where I'm taking a vector from that, sending it through transformation T1 to T1 of U, which belongs to vector space V. And then vector space V was the domain of T2, so I take that vector from V, this T1 of U, run it through T2 and get a vector from space W, which was the codomain of T2. Okay. And running it through those steps is the same as taking vector U and applying the transformation T2 composed with T1 and going straight from U to W. Right. And as I mentioned, I'm not going to, you can read this proof on your own. When you compose, if two transformations are linear transformations, then their composition will also be linear. And they show you that the additivity property and homogeneity properties would hold for the composition, so therefore it would be a linear transformation. Right. And as before, as you probably saw in a previous algebra class or pre-calculus, the order in which you compose functions generally matters. Right, T2 composed with T1 is not always going to be the same function, the same transformation as T1 composed with T2. Right. So they say that composition is not commutative. Right? The order matters. So let me show you an example here where I'll take you through how would I perform composition with certain linear transformations. Alright, so what I have here are the two linear transformations given to us in this example. So T1 is from R2 to R3. So my input is a vector with 2 components. The outputs are vectors with 3 components. And then T2 is the other way around, right, from R3 to R2. Input is a vector with 3 components, and the output is a vector with 2 components. Alright, so the first part they're asking us to do is find this composition T2 composed with T1. Alright, now if I do this, if I do T2 composed with T1, this means I'm going into function or transformation T1 first. I'm going to apply that first and then apply T2. So if I go through T1 first, that means my inputs are coming from R2. And then the output will be from R3. And then I'd apply T2 to that vector from R3, and it would give me an output from R2. So in this composition, T2 composed with T1, I'm starting in R2 and ending in R2. So this is going to be a transformation from R2 to R2. My input will be a vector with 2 components. And my output, when I'm all done, should also be a vector with 2 components. Right. So let's see what this is. So I'm going to do what's T2 composed with T1 of some vector from the domain, which again in this case the domain is R2. So I'm going to start off here with a vector with 2 components, say x1 and x2. So again, remember how this stuff works. Composition. This is the same thing as T2 of T1 of this vector from R2, x1, x2 here. So sorry, lots of parentheses. Alright, so what's happening? Again, I apply T1 first. Alright, so I'm going to apply T1 first and keep that inside there. Now, just T1's up here, so this is going to be equal to T2 of, and then when I apply transformation 1 to this x1, x2 vector, well, that's giving me, it looks exactly the same as this, so this is my output. And it's a vector with 3 components, where the first component is the sum of these two. The second component of the output is the same as the second component of the input. And the third component of the output is the opposite of the first component of the input. Right. So I've applied T1 to the input vector. And now I'm going to apply T2 to this vector here. And what was T2? Right, T2 was this transformation. But instead of x1, I'm going to replace all the x1s in this with the quantity x1 plus x2. And x2 is still x2. And then all the x3s, right, these x3s up here, I'm going to replace with the opposite of x1, this minus x1. So in applying T2, we get the following, right? So again, it takes a vector with 3 components and outputs a vector with 2 components. So in the first one here, it would be 3 times the first component. So 3 times this quantity x1 plus x2 plus 2 times the second component, right? Plus just 2x2. And I'll simplify this in a second. Then the second component is 4 times the third component of the input. So 4 times this negative x1 minus the first component. So minus this quantity x1 plus x2. And then finally minus 3 times the second component, which is still x2 here. There's the output, the final output. Now I'm going to, simplify this. You'd have 3x, distribute the 3 here. So our first component of the output in this composite function is going to have 3x1, and then plus 3x2 plus 2x2 be plus 5x2. And then the second one here, I'll be distributing this negative. We'll have negative 4x1 minus 1x1 will be minus 5x1. And then we have minus x2 minus another 3x2 be negative 4x2. And there we go. Here's T2 composed with T1 at any vector with 2 components, x1 and x2. And there we go. That's what was asked for. And again, it's a linear transformation from R2 to R2, right? Input has 2 components, output has 2 components. Okay. And if you want to play around with it, try plugging in some vectors with some actual values and see if results match. So let me actually do that. All right, and you don't have to do this, but let's find. So just one example here. What would be T2 composed with T1 at the vector, I don't know, 3, 4. Okay, now if I apply the rule I just found, we can get it right away, right? This would be 3 times the first component, so 3 times 3 minus, plus. 5 times the second component, 5 times 4 for that first component of the output. And then for the second component of the output, negative 5 times x1 would be 3 here, minus 4 times x2. And so the output for this composite transformation, when the input was the vector 3, 4, it'd be 9 plus 20, so 29 for the first component, and negative 15 minus 16, negative 31 for the second component. Right? Now let's try finding this, with the successive substitutions. Remember, this is the same as T2 of T1 of the vector 3, 4. Again, you can just make up any other example you wish. So this would be T2 of, now when I plug in 3, 4, back in the transformation T1, right, there was T1. When I plug 3, 4 into the T1, first output component is 3 plus 4, 7. Second component would be 4, and then the opposite of x1, so the negative 3. Right, and then I'll apply T2 to this, and I'm hoping I get this 29, negative 31. I better, if what I did earlier was correct, this should end up being 29, negative 31. Let's see. So applying t2 to this vector, we get 3 times 7 plus 2 times 4, and then 4 times negative 3, the x3, minus 7, minus 3 times 4, and yeah, that's 21 plus 8, 29. And then negative 12 minus 7 is negative 19, minus 12 is negative 31, and these are the same. So, I mean, that's just one example. You could have picked anything you wanted just to check, just to see, hey, is my composite function correct? All right. So there's the function, the transformation t2 composed with t1. All right, and again, it goes from R2 to R2. All right, now let's see what happens when we go in the other direction. All right, compose in the other order. So again, here were the transformations given, t1 and t2. But now this time, I want to find the composition t1 compose with t2, if I can. All right, in order to do composition, the codomain of the right function has to be the same as the domain of the left function or transformation. And that's happening here as well. Right? When I do t1 compose with t2, remember this means I would be applying t2 first. So my input's coming from R3 now. And then I'd take this vector from R3, get an output from R2, and then I would apply T1, which I could. I'd take this vector from R2 and then apply T1 to get a final output from R3. So this composite function, so right away you can see that they're different. Right? T2 composed with T1 would be going from R2 to R2. Switching them is a function from, a transformation from R3 to R3. So right away you're seeing that they're different. Right? They have different domains and different codomains, so they must be different transformations. Okay. So let's see what we get. Alright, so I'm going to take this time T1 compose with T2 of, and then now this time though I'm going into T2 first, right? My input is from R3, so this input vector will have 3 components, say x1, x2, x3. Right. So again, this is T1 of T2 of this vector x1, x2, x3. Let me get rid of that undersheet. Alright, so first, I'm applying T2. I'm applying T2, which I have here. So this now becomes T1 of, and then T2 of this 3-component vector gives me this 2-component vector. 3x1 plus 2x2, and then 4x3 minus x1 minus 3x2. And now I'm applying T1. T1 looked like this, where instead of everywhere there's an x1, I'm going to replace it with 3x1 plus 2x2. And everywhere there's an x2, I'm going to replace it with 4x3 minus x1 minus 3x2, that whole second component. Okay, so again, then my output from T1 is going to be a vector with 3 components, where the first is the sum of the 2 components, right? x1 plus x2. So we have a 3x1 plus 2x2. That's the first component of my input, plus and 4x3 minus x1 minus 3x2, right? There's the second component of my input, and they're added together to give me the first component of my output. The second component of the output is the same as the second component of the input, so the second component of the output here will be this 4x3 minus x1 minus 3x2. And then the third component of the output when I apply T1 is the opposite of the first component of the input, so it's the opposite of this 3x1 plus 2x2 quantity. All right, and I'll simplify this on the next page. So we're getting T1 composed with T2 of some three-component vector, x1, x2, x3, gives me the following output, which would be another three-component vector. Here we have 3x1 minus x1, so 2x1. There's 2x2 plus negative 3x2, so minus 1x2. And then 4x3, right, plus 4x3. Second component is this. I'm going to put them in order though, so negative x1 minus 3x2, and then plus 4x3. And then finally, distributing the negative down here, we'd have minus 3x1 minus 2x2. And then, no x3. And there we go. All right, here's what they wanted for the second part of that example, or here's what they were showing. All right, and again, clearly you can see that T2 composed with T1 is not the same as T1 composed with T2 here. So in general, composition is not commutative. And again, I'm not going to do it this time, but if you wanted to, you could plug in some actual numbers here and see what you get, and then go through it the long way and see if you get the same thing. Right, just to test out, hey, did I do this correct? And I'm just going to go back to the website and show you. Let's see. So yeah, again, I know I got the first one right, and yes, this is exactly what I got on my paper. All right, now I'll show you in a second too that there is a quicker way to do this using matrices. We'll get to that in a little bit. I'll come back to these same examples and do it using matrices. All right, so you're asked to do the same for here, this participation activity. You're given T1 from R2 to R3, T2 from R3 to R3, and T3 from R3 to R2, and asked to match the compositions. So I'll leave that to you. Now be careful this one here. It's three of them. So this means I'm running through T1 first, then T2, then T3. Alright, but again, I'll leave that to you to see what your outputs would be for each of these compositions. Okay. Alright, then we talked about properties before of transformations. When is a transformation one-to-one? When is a transformation onto? Hopefully you recall those words. These are just statements telling you that if linear transformations T1 and T2 are both one-to-one, then their composition will also be one-to-one. Same thing for onto. If two transformations are both onto, then their composition will also be onto. Right. Now the converse isn't true, right? If a composition is one-to-one, that doesn't mean that both the transformations that made it up have to be one-to-one. If a composition is onto, that doesn't mean that both the transformations that made the composition have to be onto. Alright, so these statements in this direction are true, but in the other direction are not necessarily true. Alright, so just be aware of that. Alright. So here, given, for example, applying these statements, given that this transformation and this transformation, given these two, T2 composed of T1 must be 1 to 1. Well, obviously this first transformation is not 1 to 1 because every single input is going to the same output. And if you did T2 composed with T1, every value you threw every vector you threw into T1 would go to this vector 1, negative 1, 2, and then you would just be plugging in 1, negative 1. You'd get the same output every time. You'd plug this 1, negative 1, 2 into T2, and you'd be getting the same output every single time. So many inputs would go to the same output. This is not 1 to 1. Right. And then this, must be onto. Let's see. T1 is from R4 to R3. T2 is from R3 to R3. Okay, and must their composition be onto? Now remember, to be onto means that every vector in the codomain is also in the range, right? Every vector in the codomain is an output. So I'm running through T1 first. Now let's see. Would every vector, would this be onto 3, 4? Yeah, I'd say that if you were to, again, if I'm thinking matrix-wise, if you were to make a matrix representation of this, just coefficients of x1, x2, x3, x4, you'd have 1, 1, 0, 1, negative 1, 0, 0, 0, 1, 0, negative 1, 0. There'd be 4 column vectors, but so all of R3 is definitely hit, and 3 of those would be independent. Trust me. All right, and you can check, put it in reducer echelon form, and check that 3 of those vectors would be independent. So R3 would be spanned. T1 is onto T2 from R3 to R3. You'd have 1, 1, 0, 1, 0, 2, 0, negative 1, 0. And I'm pretty sure this would be onto as well. Again, you could put the matrix representation of this into echelon form. I'd say true for this one. Right. Yeah, both of them are onto. So their composition must be onto as well. All right, now we get into the what'll make composition a little easier. Matrix representation of composition of linear transformations. So remember this standard matrices, say T1 has a standard matrix A1 and T2 has a standard matrix A2. Well, then the composition T2 composed of T1 would simply have a standard matrix A2 times A1. You just multiply the standard matrices in the same order that their composition is. All right. And then you can run through this. You can look through the proof. But let me show you an example. Okay, with matrices. So back to the same transformations here. All right. Same transformations. So, I was given this T1 earlier. Now hopefully you can see that, again, remember every linear transformation can be expressed as a matrix product, a matrix transformation. So hopefully you can see this, that T1 of x1, x2 is very simply just, I'm going to make a 3x2 matrix here where down the first column are just the coefficients of x1, 1, 0, negative 1. Then down the second column are the coefficients of x2, 1, 1, 0. And this matrix I'll call A1, right? That's the standard matrix for transformation 1. And I would take every input and multiply this matrix by that input, and it would give me the output. Right. And you can double check. Multiply these two matrices, you'll get this back up here. Right. And again, this can be done for any linear transformation. And it's very easy to see the matrices, when it's between Euclidean spaces like this, R2, R3 and stuff. And I'll do the same thing for T2. T2 of this, x1, x2, x3, since T2 is a linear transformation, I can express it as a matrix product, a matrix transformation. And I'm going to have a 2 by 3 matrix. Remember the standard matrix. The dimensions are the dimensions of the codomain will be the number of rows, so 2 rows. The dimensions of the domain will be the number of columns, so it'll be 3 columns. So I'll have a 2 by 3 matrix here, where down each column I'm going to put the coefficients of x1, x2, and x3 in these output components. So you see 3x1, negative 1x1. 2x2, negative 3x2, so 2, negative 3. And then no x3, so 0, and then 4x3. Okay, so this matrix, the standard matrix for transformation 2, I'll call A2. And if I want to plug in some input, get an output, I take this input and multiply it by this matrix. So I take this matrix and multiply it by the x1, x2, x3 input. And you can double check. Multiply this matrix by this matrix, and you will get this matrix. You will get the output from transformation 2. Okay. So when I do composition, if I know the matrix versions of my linear transformations, then the composition will just involve matrix multiplication. So let me go through it now. So here are these transformations written in matrix form. And let me do the compositions. Now they did. The first one was T2 composed with T1 of and if I do this, my input's coming from R2, so of x1, x2. So remember what happens here. This is T2 of T1 of x1, x2. And when I do the T1 first, when I apply T1 first, I'll get T2 of, and then A1 times this input vector. Right, whatever that is. Okay. And again, A1 is this 3 by 2 matrix up here. I'll write this in a second. And then when I apply T2 to this A1 times the vector, A1 times the input vector, well, when I apply T2 to some vector, I get the matrix A2 times that. So this will be A2 times A1 times that input vector, x1, x2. All right, and then A2 times A1, this is going to be the standard matrix for our composition. The standard matrix for T2 composed with T1. And let's see what happens when I get A2 times A1 here. All right, what do I get when I multiply A2 by A1? So A2 was this 2 by 3. Right, again, I'll write it again. 3, negative 1, 2, negative 3, 0, 4. There's A2. times, and then A1 was a 3 by 2 with 1, 0, negative 1, and 1, 1, 0. And then again at the end here times that original input vector x1, x2. All right, so in multiplying these matrices, A1 times A2. Now, this is a 2 by 3 times a 3 by 2, so it'll end up being a 2 by 2 matrix here. Again, that input vector just stays throughout. First row, first column, 3 plus 0 plus 0, so 3. First row, second column, 3 plus 2 is 5, plus 0 is 5. And then second row, first column, negative 1 plus 0 minus 4 would be negative 5. And then second row, second column, negative 1 minus 3 is negative 4 plus 0. Right. There we go. And so here's our T2 composed with T1 written as a matrix transformation. Now let's actually go back and look at what I did earlier in the video when I wasn't using matrices, and see what I got when I did T2 composed with T1. This is what I got earlier. Remember this earlier? This is T2, the same T2 and T1. T2 composed with T1 of some input was this. Look at the coefficients. Coefficients of x1, 3, negative 5. First column of my matrix here, 3, negative 5. Second column with the coefficients of x2, 5, negative 4. There they are there. So if you were to multiply these two matrices down here, you would get what I got earlier for the result of the composition. All right. And it's really that simple, and I feel like this is a quicker way to do composition. So then if I was composing in the other order, right, I'm just going to multiply those matrices in the other order. Right? It's really that easy. So then for the second one, if I did want T1 composed with T2, again the input will be a vector with 3 components. Since I already know my standard matrices for these transformations, to get the matrix for this composite transformation, I just take in that order, A1 times A2, whatever that matrix product is, times the input vector. All right, let's see what we get. All right, so here A1. Remember, A1 was this 3 by 2 with the 1, 0, negative 1. And the second column 1, 1, 0. And then A2 was a 2 by 3 with the 3, negative 1, 2, negative 3, 0, 4. And then times this, input vector. That's not changing, that's always sticking around. All right, and then multiplying these matrices here gives me the standard matrix for this composite. Now it's a 3 by 2 times a 2 by 3. So the result will be a 3 by 3. And again, times the input vector. Right. So first row, I'll just go through it real quick. That'll be 3 minus 1 is 2. And then 2 minus 3 is negative 1, and 0 plus 4 is 4. So 2, negative 1, 4 for the first row. Then just the second row coming up next, negative 1, negative 3, 4. And finally, negative 3, basically just the opposite of that first row, negative 3, negative 2, 0. All right. So here's the T1 composed with T2, written as a matrix transformation. And again, let me show you, let me compare this to what I got earlier. This is what I got earlier when I didn't use matrices. And look at down the first column, with the coefficients of x1, 2, negative 1, negative 3. Coefficients of x2, negative 1, negative 3, 2, negative 2. Coefficients of x3, 4, 4, 0, 4, 4, 0. Beautiful. Right, if I were to multiply these two matrices here, I'd get exactly what I got as the output for this composite earlier. So it's very easy, I feel, when you're given two linear transformations to compose them if you write them in terms of their standard matrices. I think it makes it a lot easier to do the composition in that case. Right? All right. So hopefully all that made sense. All right. Again, I feel that was easier than actually doing the composition the long way like I did earlier. All right. So that's what they're doing here for all these. Now these are different here. These are different, but they're doing the same stuff. I'll let you read these, taking you through the find the standard matrix for each of these, and they'd be 2 by 2s, both of them. And then when you compose them, you just multiply those matrices in the order that they're coming in, right? If you do T1 composed with T2, the standard matrix will be A1 times A2. If you do T2 composed with T1, the standard matrix will be A2 times A1. Right? Just pay attention to the order. All right, and then they have a. I'll let you look. Again, after watching me do that first one, I'm hoping you can do these pretty easily. You got the activity. You're given two transformations as to what are the standard matrices for the individual these T1 and T2, and then what would be the standard matrices for T2 with T1 composed with T1, and then for T1 composed with T2. And it's just a matter of multiplying A2 by A1, A1 by A2, right, to find the standard matrices. And then for the challenge activity, now this first one is just if I was to compose T1 with T2 and then plug in this vector -4, 5, what would be the output? Right? So this isn't about finding standard matrices or anything. I mean, you could, but this is just apply T2 to -4, 5. And if I do that, I'll get 1620, and then apply T1 to 1620, and there'd be -80, -5 times 16 for the first component, and then again 2 times 16 is 32, 3 times 20 is 60, 60 plus 32 is 92 for the second component. Okay. So again, that was just a matter of plugging in values, just running through the composition. And let's see what the other levels look like. Yeah, so this is the same thing, just kind of run through the composition with a couple inputs. But they're doing, this one's T1 composed with T2, this one's T2 composed with T1. You're just plugging in what are the outputs for both of those. This is the same thing, but instead of going between Euclidean spaces, you see they're plugging in a polynomial as the input, and then the output for T1 is a vector from R2, and then T2 takes a vector from R2 and gives you a matrix with a 2 by 2 matrix. Right. So this is an example where I could compose T1 with T2 with T1, right? Because if I run through T1 first, the outputs from R2, and then that'll be the input of T2. But I couldn't do the other way around, right? T1 composed with T2 would be wrong. You couldn't do it. It'd be undefined, because T2 would give me an output that's a 2 by 2 matrix, and then I couldn't plug that into T1, right? Because the inputs for T1 are polynomials of degree 2 or less. So if these are my transformations, the only way I could compose these is T2 with T1. And then again, you just have to plug stuff in and get an output here. Level 4, again, your inputs x, y, write your outputs after running through these transformations, doing T2 composed with T1. But instead of numbers, you have x's and y's, and a's, b's, c's, and d's showing up. And then finally, A is some 2 by 2 matrix here with component with entries B, C, D, E. T1 is the transformation that gives you the trace of A. Remember, the trace is just the sum of the main diagonal entries. So like the trace of this matrix would be B plus E. And T2 just gives you the transpose of the matrix. And then again, your output, right? Your output needs to be in terms of like basically B, C, D, and E, right? And if the composition doesn't exist, enter NA, right? Because look, I can do T1 composed with T2. You can do that. Because see, the output for T2 is going to be a 2 by 2 matrix, and I can plug that into T1. So you can do T1 composed with T2. But you can't do T2 composed with T1 because look, when I go through T1 first, the output's a real number, which is not a 2 by 2 matrix. So I can't plug this into T2. So I'm gonna, for that one, I'd type in just the NA that they want. This one I could actually do, right, and write an output in terms of B, C, D, or E. All right. And I think this is the final part. We'll see. Then we'll talk about inverse linear transformations, just reversing the mapping, going back to the, just reversing the mapping. Hopefully you remember what inverses are. So if you're given a linear transformation T, from U to V, and it takes input U to output V, then the inverse will take V right back to U. Right, maps V right back to U. It reverses the mapping. And you see it's called T inverse with the little -1 symbol above it. And it goes, again, just reverses, not the domain and codomain switch. Now the only kinds of, and I'm going to tell you right now, just look at your matrices. Right? If you write your linear, if you find the standard matrix for your linear transformation, if the standard matrix has an inverse, then your linear transformation will also be invertible. All right. So here, look at more stuff. Applying a linear transformation T to a vector U, then applying T inverse takes you right back to U. All right. Similarly, applying T inverse to vector V, and then applying T takes you right back to V. Right. So this may sound familiar. When you compose inverses, they basically like undo each other. You end up back where you started. All right. Now, not every linear transformation is invertible. Right? If A is the standard matrix of T and A is invertible, then T is invertible and the standard matrix of T inverse will be A inverse. Right? Since only square matrices have an inverse, the transformation matrix A must be square. And that means the vector spaces in the domain and the codomain, U and V, must have the same dimension. Right? And because the inverse of a matrix is unique, a one-to-one correspondence exists between the domain and codomain of T and T inverse. Thus, and this is a huge statement here, and we actually saw this earlier, an invertible linear transformation is an isomorphism. Right? Isomorphism. Remember, an isomorphism was a one-to-one and onto transformation that was also linear. But if you're one-to-one and onto, that means you're invertible. Okay, so for example, if they said, well, first they could ask, is this even invertible? Let me pause this. I'll write this on some paper and get to it. Okay, so here's the transformation given in this example in the text. Shows you how, again, it's got to be between, in order for a transformation to even possibly be invertible, the dimensions of the domain and codomain have to be the same, right? So these are both dimension 3, right? if the dimension of the domain and codomain aren't the same, then there's no way the transformation can be invertible. All right, so the big question is T invertible? All right, so what I'm going to tell you to do is look at the standard matrix. If the standard matrix has an inverse, then the transformation will as well. And the standard matrix for the inverse will just be the inverse of the standard matrix. Now, kind of pretty easy. Now you could do the whole thing where you take the standard basis of R3 and plug them in, and each of those outputs will be the columns of the standard matrix. Again, when it's between Euclidean spaces, it's pretty easy to determine that T of x1, x2, x3 here, this input vector is equal to some matrix, right? And it's going to be a 3 by 3 matrix, 3 by 3. And down the first column, the coefficients of x1, right, 2, 3, 2. Down the second column, the coefficients of x2, 3, 3, 4. Down the third column, the coefficients of x3, 1, 1, 1. Maybe that matrix, times the input vector. And here's the standard matrix, I'll call it A. Right, there's the standard matrix for this this transformation. So asking if T is invertible is the same as asking, is the standard matrix invertible? Right, or non-singular? Does it have an inverse? All right, now you could just, you could put join the identity matrix on this, put it in reduced echelon form, see if you can find an inverse. You could take the determinant of this, and if the determinant's not 0, then it's got an inverse, and then you can find the adjoint the adjoint matrix for this using the transpose of the cofactor matrix, and then multiplying by the reciprocal of the determinant. Right, there were several ways to find the inverse if it existed. But I'm just going to pull up a calculator. All right, we're at that point now where I've seen you do lots of elementary row operations and finding determinants and whatnot. We're past the point where that's the important stuff now. Now the more important things are on transformations. So you can just have a calculator do this now if you want. So pull up the calculator. And hopefully remember how to enter a matrix. So I go, second matrix menu over to edit, and this is a 3 by 3 matrix we're making. And I'll put these entries in. I'll come back when I'm done. Alright, so I've entered all 9 entries. I get out of here, quit. Now I'll find the inverse. Go back to the matrix, hit A. That was matrix A, and then just hit this inverse button right below the matrix, the little -1. And if it comes back with an error, then I'll know it's not invertible. But it doesn't. Right? There is an inverse. So, yes. That means that T is invertible, and T inverse then, right, T inverse of x1, x2, x3 would be the following. I just use A inverse, which is on my calculator right now. T inverse would be this matrix, right, which is A inverse, the inverse of T's standard matrix, which has -1, 1, 0, -1, 0, 1, 6, -2, -3, times the input vector, which again would be T inverse would just reverse the mapping, right? So it's still going from R3 to R3 here. Right, it's still doing that. and then times, this inverse matrix, this standard matrix times the input vector. And if you want to multiply this out, you'd get the following. Right? You'd have negative x1, 6x1, plus x2, minus 2x2, and then no x3, plus x3, and then minus 3x3. If you were to actually multiply these matrices, you'd get this output vector. All right. And if you were to compose these, they'd undo each other. All right, but let's actually test it out. Let's test to see if these are inverses. All right. So I'm just going to go over some examples. All right. So first, I'm going to pick a vector, t of let's just do a simple 1, 1, 1. Let's find t of 1, 1, 1. All right. So let's go back to t. All right. So if I replace all my components with 1, the output is going to be 2 plus 3 plus 1, that'll be 6, and then 3 plus 3 plus 1, will be 7, 2 plus 4 plus 1, also 7. So I get an output of 6, 7, 7. Now what I'm going to do is take 6, 7, 7 and plug this into t inverse. And hopefully it takes me right back to negative 1, 1, this 1, 1, 1. So I'm taking t inverse of 6, 7, 7. And again, if they truly are inverses, I should just get 1, 1, 1 back. Well, let's see. Using that inverse matrix, I got a nice rule here for t inverse. Let's see if this actually works out the way I want it. All right, so plugging in this 6, 7, 7, you could do it. You could multiply by the matrix, or just go into my rule over here. So I'd have, what? Negative 6 plus 7, 1. Negative 6 plus 7 again, 1. And then 36 minus 14, right? 2 times 7. 36 minus 14 would be 22, and then minus 21 would be 1 again. Hey, looks like that's working out, right? It looks like t inverse, composed with t of some vector is just that vector again, right? I mean, I know that's only one example, but that should be happening all the time. Right. And the same goes the other way around. What if I did the other way around? Another example. This time I'll plug in the t inverse first. Put in some 3. I'll just make it like maybe 1, 2, 3. Something simple. Let's plug in 1, 2, 3 to t inverse. Right. So again, using my rule here for t inverse that I found with the inverse matrix and all that. So negative 1 plus 2, 1. Negative 1 plus 3, 2. And then 6 minus 4 is 2. Minus 9 is negative 7. All right. So when I plug 1, 2, 3 into t inverse, I get 1, 2, negative 7. Now let me take this 1, 2, negative 7. Let me plug this into t, and hopefully I get 1, 2, 3 back. All right, it'll take me right back in. So what's t of the vector 1, 2, negative 7? So going back to the rule for t up here. Let's see, we'd have 2 plus 6 is 8, plus negative 7 is 1. So far so good. Then 3 plus 6 is 9, plus negative 7 is 2. Again, so far so good. I want 1, 2, 3. Then 2 plus 8 is 9. No, 2 plus 8 is 10. Wow. 2 plus 8 is 10, plus negative 7 is 3. Hey, took me right back. So it looks like t composed with t inverse Now I know this is just one example, but this should work out for all of them if I did everything correctly. When I compose the inverses in the other order, my input goes right back to where it started from. Great. But yeah, so just, again, if you're asked, is a certain transformation invertible, find the standard matrix and, is the standard matrix invertible? Because the answer to that question will be the same. Okay. So they're doing all this here. All right, now they actually went through and again, you could do it. They just jumped to it. Like I said, I don't really mind if at this point you're just using your calculator. Save you a little time. All right. So here we're given a bunch of transformations, linear transformations. Now look, T1 goes from R2 to R3. The dimension of the domain and codomain aren't the same. So this can't be invertible. So T1, it doesn't matter what it looks like. Now T2 is from R2 to R2, so it could be invertible, right? The dimension of the domain and codomain are the same, so it could be invertible. Now the standard matrix would be 6, 3, negative 2, negative 1. All right, 6, 3, negative 2, negative 1. Now the determinant would be negative 6 minus negative 6. The determinant of this standard matrix would be 0. So the matrix would not have an inverse, meaning this transformation does not have an inverse. T2 is not invertible either. And T3, R2 to R2, the dimensions are the same. It could be invertible. The standard matrix would be 3, 1, 5, 2. The determinant would be 6 minus 5. The determinant's not 0. The determinant of this 2 by 2 matrix would be 1, meaning that it is invertible. And if you wanted to find the inverse, you just find the inverse matrix and use that as the standard matrix for T3 inverse. But T3 would be invertible, and they show you that all here. All right. Okay. All right. And then if you want the inverse of a composition, so if T1 and T2 are invertible linear transformations, isomorphisms, and A1 is the standard matrix of T1 and A2 is the standard matrix of T2, then T2 composed with T1 inverse is T1 inverse composed with T2 inverse. So they switch the order and take the inverses for the inverse of a composition. And the standard matrix would be A1 inverse times A2 inverse. I hope this rings a bell. Remember the inverse of a product? We talked about this way back when. The inverse of a product of two matrices is the product of their inverses, but reversed. So A2, A1 inverse is A1 inverse, A2 inverse. And the same thing goes for compositions. All right, so they give you some examples here. So I'll do this one last example on some paper. Okay, so here are the two transformations given to us. Now T1 of x1, x2 here. Easily written as a matrix transformation, right? It would be a 2 by 2 where you have negative 3, 5. First column, 1, negative 2 for the second column. Right, there's your standard matrix, A1. And same thing for T2. That would be, again, most of these linear transformations between Euclidean spaces are really easy to write as a matrix transformation. And again, a 2 by 2 standard matrix. First column 5, 2, second column 7, 3. And this is A2. Right. All right. So if I want to compose these and find the composition of their inverse, well, first let me look at the inverses of these. Now, A1 inverse, right? The determinant is 1. Now they're giving us some nice matrices here whose determinants are 1. Remember, A1 inverse, right, inverse of a 2 by 2 matrix is really simple. It's the reciprocal of the determinant, which would be 1. And then you just switch the main diagonal entries and take the opposites of the other two off diagonal entries, right? So this would be A1 inverse, and same thing for A2 inverse. This A2 has a determinant of 1 as well, 15 minus 14. So the A2 inverse is 1 times, and then again switch the main diagonals, 3 and 5, and then take the opposite of the other two. Okay. And yeah, so I got the inverses, and then we can say what T1 inverse is, right? So T1 inverse of x1, x2 would be this A1 inverse times the input vector, and T2 inverse, right, the inverse of this transformation, would also be easily found, right? T2 inverse of some vector with 2 components would be A2 inverse 3, negative 7, negative 2, 5 times x1, x2. Right. Okay, so I've got the inverses of each transformation individually. All right, but we're not asked for all that. We're asked for, well, what if we compose these, right, and wanted the inverse of that? All right, so let's compose them in one order. All right, I'll do this order here. What's T1 composed with T2 of x1, x2? Now we saw this earlier. All right, a very easy way to find the composition is to multiply the standard matrices, right? This would just be A1, right? A1, which was negative 3, 1, 5, negative 2, times A2, right? So times 5, 7, 2, negative 3, and that'll be the standard matrix, and then times the input vector. So when I multiply these 2 by 2 matrices, I get the following, right? So again, you can use a calculator if you want, but it's only 2 by 2, so they're not bad. So negative 15 plus 2, and negative 21 plus 3, and then 25 minus 4, and 35 minus 6. All right. All right. Now, there's T1 composed with T2. All right. And I'll call this matrix just plain old A. All right. Now, if I want the inverse of this composition, now since we already have the standard matrix here, we could just find the inverse of this. And remember, this is A1 times A2. Both of these have a determinant of 1. And remember, the determinant of a product is the product of the determinants. So this matrix also has a determinant of 1. So A inverse would just be, switch the main diagonals and take the opposite of the other two, right? Positive 18, negative 21. Okay. So if I wanted the inverse of this, right, T1 composed with T2 inverse, it's this matrix as the standard matrix. Well, what that whole theorem, what the previous page on the website was saying on the Zybooks, that I could also have found this by, when I do T1 composed with T2 inverse, I could have also found this matrix by taking the inverse of the A1 times A2, right? Now remember, A1 times A2 is the standard matrix for T1 composed with T2. If I take the inverse of that, remember the inverse of a product of two matrices is the product of their inverses reversed. And I had these down earlier, right? I had A2 inverse and A1 inverse written down earlier, and what we're going to see is that it's going to be equal to that matrix there, the matrix for that inverse of the composition. Let's see. A2 inverse that I had earlier was this. 3, -7, -2, 5. And then A1 times A1 inverse, -2, -1, -5, -3. And let's see that that is actually equal to this, the standard matrix I found for, T1 composed with T2 inverse. Let's see, you'd have -6 plus 35 would be 29. -3 plus 21 would be 18. 4 minus 25 would be -21. And 2 minus 15 would be -13. Saying that the product of these two is that standard matrix. So that's all they were saying. You could find it a long way like I did here, like the way you usually would. Or if you want to find the standard matrix for the inverse of a composite function, just take the standard matrix for each of those inverses, but multiply them in reverse. Okay. All right, and then you could do the same for if you wanted T2 composed with T1 inverse. Their standard matrix would be A1 inverse times A2 inverse, right? Just reversing that. Okay. Again, you can read through the example here where they do all that. All right, and then you're asked to do the same. Find well what's A2, the standard matrix for T2. What's A1 inverse, right? So the standard matrix for T1, but inverse, T1 inverse. Standard matrix for T2 inverse. And then what would be the standard matrix for T2 composed with T1 inverse? That would just be A1 inverse times A2 inverse, right? If you know what they are. Okay, so I'll leave this to you. And then finally you have your additional exercises. Again, some of these are assigned to you, some are not. I would still recommend looking at all of them, right? Getting more exposure to the material, getting hopefully better at it through more practice. And you do have the solutions you can fall back on. You can look at them, when you're struggling, see how they're doing things. But please, try to work out the problems on your own first. Try to work on it, figure it out before you look at the solutions. Because if you're just copying solutions down, you're not going to learn anything. If you're just not trying and just copying them. And I hope this video helps guide you through this section here. Obviously, if you have any questions, just send me a message and I'll get back to you as soon as I can. And yeah, thank you very much for watching.